Bismillahirrahmanirrahim. Okay, now we will solve chapter 20, recitation problems. As you know, we already solved these problems in class, right? So these two problems were already solved in class. So you can solve them again if you want. Now let me go to this problem. So read the problem carefully. What do we have here? I give you the number of mole. So 3 mole, so Na is equal to 3 mole. Sample of an ideal monoatomic gas. So I know that basically, I know Cp, half of R, I know Cv, 3 halves of R, and I know gamma. If I need it, it's just 5 divided by 3. So a 3 mole sample of an ideal monoatomic gas undergoes the process shown in the figure 4. So this is the figure 4. What do I have in the figure 4? I have the temperature in Kelvin versus entropy, okay, in Joule per Kelvin. You remember, in general, we were discussing in class about PV diagram. So this is what we call a TS diagram, temperature entropy diagram. Now the question is very simple. How much work is done by the gas in this process? I give you N is equal to 3. So how can you solve this problem? Well, so here, the key is here, okay? Students are not used to this type of problem. That's why I did this problem, okay? So here I have a TS diagram. You remember, what is the entropy? We know that the change in entropy delta S for a reversible process is integral between initial to final state of dq divided by temperature. So this is by definition the change in entropy, okay? So here the entropy is changing, the temperature is changing. Now, let's just look at the, this is the integral form of the change in entropy. So what is the small change in entropy? ds. It will be just dq divided by temperature. Do you agree with this? Yes, this is just, the integral form. And this is a differential form here. Okay. Integral form, the change in entropy, macroscopic change in entropy. This is the element of entropy, okay? Differential form, integral form. From this, I can just write that dq is just TdS. That means if I integrate now, I will have Q, which is the heat exchange during a process, is just an integral between initial and final state of temperature ds. Okay. In other words, the heat exchange during a process is just an area under the curve. But an area under which curve? Temperature versus entropy. Okay. Good. Now here I have temperature versus entropy curve, T versus entropy curve, T versus S or TS diagram. You see, I start by here. This is my initial state and this is my final state. So the heat, Q, will be what? Will be the area under the curve. Okay, so which area? I'm talking about this area here. Okay, so it's an integral between 10 Joule per Kelvin to 40 Joule per Kelvin of T ds, basically area as I showed it here. So what is this area? It's equal to, so, okay, it's a parallelogram, okay? So you know that I know this. I know this. Okay. So it will be T final plus T initial. So I'm adding the two bases, the area of a parallelogram, multiplied by this height here, which is delta S. Okay. Multiplied by delta S divided by 2. Okay. Area of a parallelogram. You remember? Remember from high school or prep year. If I know this, if I know this, and if I know this, so what is the area here? Will be B plus C multiplied by H divided by 2. So that's what I used here. Okay. So I know what's the area under the curve. I know what is the heat. So let me write it properly. So T final is 250 Kelvin. T initial is 500. So Kelvin times, what is delta S? Of course, delta S will be 40. 40 minus 10. And this will be joule Kelvin. So the Kelvin will go away, now divided by 2. So you calculate this, and this will give you the heat. Okay. And of course, this heat is a positive one because it helped increase my entropy. Okay. Okay. The entropy, the change in entropy has the same sign as the heat. Okay. So here the heat is absorbed, if I remember correctly. So if you do the calculation, you get 11,250 joule. Okay, this is the heat. Now, still, that's not the question. The question is how much work now is done by the gas in this process. So you know the first law of thermodynamics. Change in internal energy is just equal to the heat minus the work. Okay. That means that the work is just the heat minus the change in internal energy. So we already calculated the heat minus the change in internal energy. Remember, internal energy is just NCVP. So change in internal energy is NCV delta T. So N, I know it, 3 mole. CV, I know it. It's basically 3 divided by 2 R. And I know delta T between the initial and final. Okay. So it will be T final minus T initial. What is it? T final is 250 Kelvin. T initial is 500. So I take it and I will put it here. Okay. And then I will get the right answer. So what should be the right answer? This. Okay. Is it clear? So this is also an A+ question or an A question. Okay. Because you are not used to this. Okay. Good. So it's a TS diagram. As we said, ds is dq divided by t. That means that q is just the integral of t ds. Basically, this is an area, under the curve of t versus s, time, temperature versus entropy. And we get the heat. Then we use the first law of thermodynamics to get the work, knowing that change in internal energy is just NCV delta T. Is it clear? Excellent. Now let's go to the next problem. Read the problem carefully. So the problem reads, a heat engine takes an ideal diatomic gas through the cycle shown in this figure 5. So I have a heat engine and it takes an ideal diatomic gas. So basically I know Cp is 7/2 of R, Cv is 5/2 of R, and I know gamma, if I need it, is just 7 divided by 5. Basically Cp divided by Cv. Okay, now it's a heat engine and it takes a gas through a cycle. Now, So if the work done in one cycle is this, so I give you the work is 615 joules. What is the efficiency of the engine? Okay. So it's a heat engine, thermal engine. So thermal efficiency is just the work, absolute value, of course, divided by absolute value of QH. So I know work. So QH is what I want. Okay. So let's get QH. Okay. The heat that the heat engine is taking from the environment. So first, remember, here I give you a PV diagram. Of course, and the cycle is rotating, is going, of course, clockwise. So the work is, as we said, is this area here. Okay. And it's positive because I'm rotating clockwise. The cycle is rotating clockwise. Okay. So it's work done by the gas. That's why it's an engine. Okay, now let's identify now. So here, let's start by B first. I go from B to C, then C to A, and A to B. So this is not a Carnot engine. It's just a heat engine. Okay? But I give you a cycle. So let's identify. So from B to C, we have a constant pressure process. So it is in this that, let me put it in another color here. Okay, let me put it in blue. So in the process BC, I take QH from the environment. Okay. So the question is, what is this QH? For the sake of completeness, from C to A, am I taking heat or am I releasing heat? Okay, so I'm releasing heat actually. Let me call that small q. Okay. Because I'm going from a hot temperature to a lower temperature. So heat is released here. So Q here is positive, it's taken by the gas. This small q here is negative. It's released during this constant volume process. Okay, it's a heat removal process. And finally, from A to B, what do you think? Might be an adiabatic compression. Okay, so heat is released as well, QL. Okay. Good, but I did not ask you about this Q here in this side and this QL. Okay, but all I'm asking you is what is the QH? What is the heat that I take from the environment in the cycle? So what is QH here? Well, very simple. QH is happening at a constant pressure process between B and C. So QH is just Q, B, C. So constant pressure process, it will be just N, Cp, delta T. Okay. So I know Cp. Cp is here. Now delta T is what? Let's get it. We know that we have an ideal gas. So PV is equal to nRT. Okay. Now that means T is just PV divided by nR. Now delta T. Now here in this process here, which is an isobaric process, constant pressure process, T is constant. So delta T will be just P, I get it out, delta V divided by nR. Now, of course, this, I will take it and I will plug it here. So my QH will be NCP, now delta T, I will have P, delta V divided by nR. And N goes away, and I will have Cp divided by R, P delta V. Okay. In other words, Cp divided by R will be 7/2. P, I know it. It's this constant pressure here. So let me write it down, 4 10 to the power 5 Pascal. What is my delta V? My delta V will be this V minus this V. So basically 0.01 minus 0.005 meter cube. And you calculate this. How much do you get? So you get it here, and then I come here, I write, and I calculate the efficiency. I take this, and I put it here. So I got 7,000 joule. So here I put 7,000 joule. Okay. Joule divided by joule, and I have this now. My efficiency will give me 0.088, basically this, okay, 8.8%. Good. So analyze this very well. Okay, as I said, this is QH, this is Q negative, and of course QL is negative because it's released. Okay. Good. It's a very good problem. Next, as all my recitation problems. Mashallah. Okay, now let's solve this problem now. So we have a Carnot engine. Now it's a Carnot engine. The previous problem, I just said it's a heat engine. It's not obviously a Carnot engine, okay? It's not made up of 2 adiabatic processes and 2 isothermal processes, okay? So that's not what I have here in this problem. So it's not a Carnot engine. Now the next, it's a real engine, let's say. So this is a Carnot engine. So it's an ideal Carnot engine. It operates between 2 reservoirs, and I give you TH, temperature of the hot. Okay. This is TH, and this is TL, temperature of the hot reservoir and temperature of the cold reservoir. Okay. So now the question is, if the engine absorbs 100 joule of heat per cycle from the hot reservoir, what is the work output per cycle? Okay. So as I said, pH is equal to 600 Kelvin. You always put this temperature in Kelvin, and TL is equal to 300 Kelvin. So we know that for a Carnot cycle, a Carnot engine, well, efficiency is equal to what? What do I want to maximize? I want to maximize the work divided by QH. As we said, this is for any engine, by the way, okay? So this, you know, that work is just QH minus QL. All these formulas are in your formula sheet, divided by QH. So that gives you 1 minus QL divided by QH. And as we demonstrated in class, before I have now. So all this is true for any thermal engine, let's say, okay? Now, this is true for any thermal engine. Any heat engine. Now this efficiency is just 1 minus TL divided by TH. And we have demonstrated this in class using the entropy, okay? Delta S is 0, so we demonstrated that QH, we derived that QH divided by TH is just QL absolute value divided by TL. Okay, so this ratio here, just give me this. So I know the efficiency of my engine. So what is the efficiency of my engine? 1 minus basically 300 divided by 600, which gives me a half. So I have an efficiency of 50%. Okay. So this is equal to work divided by heat, input heat. Okay. So I know input heat, by the way. What is the input heat? The input heat is 100. So that means that the output work here is just half of 100, which is 50. Is it clear? Okay. Very simple. Okay. Good. Now let's go to the next problem. And by the way, all these formulas are in your formula sheet. You just need to know what I want. So here I want work output. Okay. I want this. I know this. Okay. And I know these temperatures. Second problem. How much work must be done by a Carnot refrigerator? So now I have a Carnot refrigerator to transfer 1 joule as heat from a cold reservoir at -7 degrees Celsius to a hot reservoir at 27 degrees Celsius. So I know TL. TL is -7 degrees Celsius. Of course, I put it in Kelvin. So it will be -7 plus 273 Kelvin. What is the hot? pH, high temperature reservoir, it's 27 degrees Celsius. So I know that it will be 273 plus 27. Good. Now, it's a Carnot refrigerator. So what is the coefficient of performance, K, for a Carnot refrigerator? If you remember, it's in your formula sheet. What I want to maximize is QL, and what I want to minimize is the work. Okay. So this is equal to what? It's equal to QL. It's in your formula sheet. Now this is QH minus QL. Okay. And knowing that in a Carnot refrigerator, I have this relationship. So this will just give me, as it's in your formula sheet, TL divided by TH minus TL. Good. So now let me calculate this. What is the coefficient of performance? I know TL and I know TH, so I can get easily what is the coefficient of performance. Okay, so the coefficient of performance will be given by TL, which is 266, divided by TH, which is 300, minus 266. And if you calculate it, it gives you 7.8. Okay, that's the coefficient of performance of my Carnot refrigerator. But I know already that this is equal to QL, which is the heat, that I am removing from the cold reservoir in absolute value. This is equal to 1 joule divided by the work. So work will be just coefficient of performance, will be just heat removed, which is 1 joule, divided by coefficient of performance, which is 7.8. You do the calculation and you get 0.12, 7, etc., etc. In two significant figures, it will give you just 0.13 joule. Okay, clear? Now, if I want to calculate QH, how can I do? Well, I know that work is just QH, absolute value, minus QL. So you know that QH will be just work absolute value plus QL. So I know the work, 0.13 joule. I know QL, which is 1 joule. So QH will be just 1.3 joule. Okay. By the way, this is a coefficient of performance of a Carnot refrigerator. I will talk about heat pump in class, heat pump. Okay. But I'll talk about this in class, inshallah. Okay, now Next, we have also a Carnot refrigerator, which is operating between 20 degrees Celsius and minus 20 and plus 20. So it extracts heat from the cold reservoir at the rate of this. Find the rate at which heat is exhausted outside the refrigerator. So write down your formulas and get me the answer. Okay, let's read it again. So we have a Carnot refrigerator. It's an ideal refrigerator. It's operating between 20 degrees Celsius, minus 20, and plus 20 degrees Celsius. So in other words, I'm giving you TL, which is just minus 20 degrees Celsius. I put it in Kelvin, of course, plus 273. So this gives you 253 Kelvin. And TH is just 293 Kelvin, basically plus 20 degrees Celsius. Okay, so this Carnot refrigerator, which is an ideal refrigerator, is extracting heat from the cold reservoir at a rate of 200 watt. So it's extracting heat from the cold reservoir at this rate. So this rate of 200 watt is just QL divided by T. Okay. So this is the rate at which I'm extracting heat from the cold reservoir. Now, what's the question? Find the rate at which heat is exhausted outside the refrigerator. So basically now what I'm asking you is to find QH divided by the same T. What is QH? The amount of heat exhausted, basically released outside the refrigerator per unit time. Okay. Now, of course, in between, what is the work done on the refrigerator per unit time? Okay. Good. Now, let's solve it. I give you TL and I give you TH, so I can calculate the coefficient of performance of my ideal Carnot refrigerator. As we said, K for Carnot refrigerator is just, let me write first the formula. TL divided by TH minus TL. So I will have 253 Kelvin divided by 293 minus 253, basically 40. So you will have a coefficient of performance of 6 point, if I don't, so I think 6 point something. Okay, let's calculate it very quickly. 253 divided by 40. Okay, 6.325. This is my coefficient of performance of this Carnot engine, Carnot refrigerator, sorry. Okay, so this coefficient of performance, K, which is 6.325, is equal to what? What is the coefficient of performance for a Carnot refrigerator? What I use, which is QL, divided by what I pay for, which is the work. Okay, good. Now, let me divide by time here. Same time. Let's say the time of a cycle or time, any time per unit second, let's say. Now, QL divided by T, this is just, as we said before, 200 watt. So that means I can get what is the work done per unit time. The work done per unit time will be just the heat extracted from the cold reservoir per unit time divided by the coefficient of performance. So it will be 200 divided, watt, of course, divided by 6.325. So can you get me the power or the work per unit time? So 200 divided by 6.325. So the work per unit time is 31.6 watt. So this is the work per unit time. Okay, the work that I have to do on my working substance of the refrigerator. Good. Now, the question is still not that. The question is to find the rate at which heat is released outside the refrigerator. We know that the work is just absolute value of work is just absolute value of QH minus absolute value of QL. Okay. So that means that QH, as we said before, is just basically absolute value of QL plus absolute value of work. Now I can do it per unit time. I divide by the same time, divide here by the same time, and I divide here by the same time. In other words, the rate at which heat is exhausted outside the refrigerator is just equal to this, and we know this already. QL divided by T was given, so basically 200 watt plus work per unit time, or the power that I'm providing to the refrigerator, which is 31.6 watt. So this gives me a QH per unit time of 231.6 watt. In kilowatt, it will give me just 0.23 kilowatt. Okay, and that's the first answer, of course. So these problems are not difficult, but you just need to know what is given and what is asked, and you go step by step. In general, you go by the coefficient of performance. You get, here we got work divided by time, and then from that, we get QH divided by time. Okay? So step by step, not very difficult, but you have to be careful. Is it clear? I hope yes. So let's read this problem very carefully. Q7. So one end of a metal rod is in contact with a thermal reservoir at 700 Kelvin. And the other end is in contact with another thermal reservoir at 100 Kelvin. The rod and the reservoir make up an isolated system. Now, if this amount of heat is conducted from one end of the rod to the other end of the rod uniformly, what is the net change in entropy of the two reservoir system during this process? Always draw, okay? You draw, we are in physics, you draw. We have a metallic rod. So this is my metallic rod, as you can see. Okay. So this end is at T hot, 700 K. And this end is connected to another thermal reservoir. Let me call it T cold, TC, which is 100 Kelvin. Good. Now rod plus two reservoir, everything here is an isolated system. Now, if Q, so now there is an amount of heat. Let me write it with another pen, with another color here. So Q is the amount of heat conducted from the hot end to the cold end. And Q here is equal to 8.5 10 to the power of 3 joule. The question is, what is the net change in entropy of the two reservoirs during this process? So these two reservoirs here a reservoir by definition. So the absorption or release of heat will not change much the temperature, but it will change the entropy. Okay? But the temperature will be constant. So let me calculate the change in entropy for the hot reservoir. It will be integral between initial and final, dq divided by T. But T reservoir is fixed and is equal to the hot reservoir, temperature of the hot reservoir. So it will be Q released or lost by hot reservoir divided by what? pH. Because this T is constant, it's a reservoir. Okay, so I put it out and this integral will be just Q lost by the hot reservoir. But the Q lost by the hot reservoir will be just this. So you'll have minus. So this amount of heat conducted through the rod is provided by the hot reservoir. So Q lost by the hot reservoir is just minus 8.5 10 to the power 3 joule divided by T hot. What is T hot here? 700 Kelvin. And I get a change in entropy of minus 12.1 joule per Kelvin for the hot reservoir. Now, what is the change in entropy for the cold reservoir, the low temperature reservoir? So it will be, of course, integral between initial and final of dq divided by T. But now this T cold is constant, so I put it out. So I'll have Q absorbed by the cold reservoir divided by the temperature of the cold reservoir. What is the Q absorbed by the cold reservoir? It's just this amount of heat. It's absorbed by the cold reservoir. So I will have plus 8.5 10 to the power 3 joule divided by 100 Kelvin. You calculate it and you get plus 85. That's what I got, plus 85 joule per Kelvin. So what is the net change in entropy? Delta S of the system made of the two reservoirs will be just delta S H plus delta S C. Okay, 85 minus 12.1. And this will give you, of course, plus 72.9 joule per Kelvin as the answer here. Okay, good. Now let's look at the second problem here. Let me erase this. Okay, let me erase. Now we have a freezer which hold N is equal to 5 mol. So N is equal to 5 mol of an ideal diatomic gas at 25 degrees Celsius and at under 1 atmospheric pressure. Okay, the 1 atmosphere. So I have an ideal diatomic gas. Basically, CV is 5/2 of R. CP also, I know it, of course, 7/2 of R. Okay, so this is my initial state. So N is equal to 5, and this is fixed. My initial state has a temperature T1, which is 25 degrees Celsius. I put it in Kelvin, so 298 Kelvin. And what is the volume? I did not talk about the volume, but you will see. And then I know the pressure. This pressure P1 is 1 atmosphere. Okay, so basically, let me write it 1 atmosphere, which is 1.01 10 to the power 5 Pascal. Now the question is, so this is my state number 1. What is the change in entropy if the gas is cooled to minus 18 degrees Celsius at constant pressure of 1 atmosphere? So I have now my state 2. Pressure 2 is constant, is equal to pressure 1, is equal to 1 atmosphere. So it's a constant pressure process. Now, what is the temperature? The new temperature, of course, is minus 18. So minus 18 plus 273, and I get it in Kelvin. So I get 255 Kelvin. Okay, now what should be my volume 2? I don't know it, but I can get it as I get volume 1. Now the question is this: during this process from 1 to 2, what is the delta S? What is the change in entropy? So what do you think? The change in entropy will be positive or negative? Of course, it will be negative because I'm cooling down the gas. Okay. Okay. Good. And this doesn't happen naturally because I have to cool it because I have a freezer. So I am doing a work. Okay. So there is a work, it's a freezer. So the change in entropy for the gas can decrease. But of course, the overall entropy of the whole system is positive or equal to 0 if it's reversible. Anyway, so here, change in entropy, delta S of the gas will be negative. So that's what I want here. So it's an ideal gas. As you know, we already demonstrated that for an ideal gas. Let me write it here. Change in entropy, delta S. We demonstrated this and we derived this, of course, is NR logarithm of V final divided by V initial plus NCV ln of T final divided by T initial. And this is in your formula sheet, and we demonstrated, we derived this already. Okay. So here, what do I know? Of course, I know N. Okay, N is equal to 5. So this I know it. CV, I know it. Okay. So as you said, N is equal to 5. CV is 5 divided by 2R, which is 8.31 joule per mole per Kelvin. Now, what is T final? Well, T final is just this, T2. What is T initial? T initial is this. So this part, I know it already. Okay. So let me write it down with another pen. So the change in entropy delta S and CV ln of T2 divided by T1. This part, I know it already. I know everything. 5 halves of this, of course, multiplied by this. Now the second half is this. I need to know, I know N, I know R. Now I need to know what is V final divided by V initial. What is V final? By the way, it's V2. What is V initial? Is V1. So I need to get the ratio of V2 divided by V1. Well, what do I know? I know that this process is a constant pressure process. So what does it mean? Of course, I know that P1, T1 is equal to NR T1. And here I know that P2, V2 is equal to NR T2. Now, if I take the ratio of this, let's say this is equation 2, this is equation 1. Of course, I will have P2 divided P2V2 divided by what? P1V1 is just equal to NR. We'll simplify and I'll just have P2 divided by T1. But you remember P2 is equal to P1. Okay, because the pressure is constant. P2 is equal to P1. So as you know, this is a constant volume process. I'm in constant pressure process. I know that V2 divided by V1 is just T2 divided by T1. Okay. So I know also the second part now. And then I calculate. So delta S will be just N R ln. So V2 divided by V1 will be just T2 divided by T1 plus NCV ln T2 divided by T1. Let me put the numbers N is equal to 5, R is 8.31, ln T2, I know it already, 255 divided by T1, 298, plus N, which is 5, CV, I know that is a diatomic ideal gas, so 5 half of 8.31, ln T2, which is T55 divided by T98. When you calculate this, it will give you minus 22.7 joule per Kelvin. Okay, which is this. Okay. Good. Is it clear? Okay, good. Next. Let's solve this problem now. So let's solve this problem, which is extremely important, okay? It summarizes chapter 18, chapter 19, and chapter 20. So everything that we have done in thermodynamics will be reviewed in this problem. So this was a quiz. Of course, if I give you this type of quiz, I will give you 30 minutes at least. Now let's read the problem, and it's extremely important. So the cycle followed by a heat engine. I have a heat engine. It's not a Carnot engine because that's an ideal engine. So here I have a real engine, a real heat engine. Okay. And I have what? 3 processes: an isothermal process, a constant pressure compression, and a constant volume heat adding. Good. So this heat engine is a real engine. It uses a number of mole equal to 2 of an ideal monoatomic gas, as shown on the right. So N here is equal to 2 mole. You write it down. And then I have an ideal monoatomic gas, meaning, of course, I have CV, which is 3/2 of R, and I know CV, which is 5/2 of R. If I need gamma, I know that is 5 divided by 3. Good. So in every cycle, so the cycle is I'm going from A to B, following this isothermal process. I did not tell you what the temperature is, but you can get it easily. And then I go from B to C, isobaric process. And then I go from C to A, isovolumetric or isochoric process. And then my cycle is complete. Okay, and I end up at A. As I said, this is a real engine. So its efficiency will be much less than the Carnot engine working at the same TH and TL. But here, let's go step by step and then we'll solve the problem. So in every cycle, calculate the heat along the path AB. So first, let's calculate the heat along the path AB. It's an isothermal process, okay? So for an isothermal process, I know how to calculate the heat. But let's do it again. So A, I want Q AB. It's an isothermal expansion. So it is QAB. Is it positive or negative? What do you think? It's positive. And we'll show it just in a second. So for the isothermal process from A to B, let's calculate the change in internal energy from A to B is equal to 0. Why? Because it's an isothermal. Change in internal energy is also always NCV delta T. But the delta T is 0, so it's the change in internal energy along an isothermal is 0. Now, if I use first law of thermodynamics, change in internal energy is QAB minus work AB. So that just gives me that QAB is equal to the work AB. Now, what is the work AB? We already calculated this. I will not go through the integral PdV, but we already demonstrated that for isothermal, this is equal to N or T ln of V final divided by V initial. And this is in your formula sheet, by the way. Okay. Now, what is nRT? I know that T is constant, so nRT is a constant. When I have an isothermal, PV, which is equal to nRT, is a constant along the isothermal. So that means nRT is just PA VA, which is also equal to PB VB. So this nRT, I will replace it by PA VA ln of V final. What is V final here? Of course, it's VB divided by VA. So let me put the numbers. So PA, what is the pressure A? Is 5 atmospheres. 5 atmospheres, so 5 multiplied by 1.01, 10 to the power 5 Pascal. What is VA? VA is 10 liters. So it will be 10 to the power minus 3 meter cube. I put everything in SI unit, and ln, now the ratio, well, it will be VB, which is 50, divided by 10. So here I don't put it in meter cube because I know that it's a ratio and it will cancel out. So let's calculate this. If you calculate this, how much do you get? So you get 8,127.66 joules. And of course, it's positive. Okay. So during this isothermal process, I have heat absorbed. Okay. So it's going this way. This is QAB. It's absorbed by the gas. Good. Now let's go to the next question. The next question is now to calculate the heat along path BC. So path BC is this path, right? Isobaric compression. So it's a constant pressure process. So B, what is QBC? So how do we calculate QBC? Constant pressure process. So heat is just N Cp delta T. Okay. And this is very important. And we already discussed this. The heat depends on the path. And here the path is constant pressure. So it will be number of mole Cp, which is specific heat at constant pressure, multiplied by delta T. Good. Now, how to get delta T? It's not explicitly given. We can get it. PV is equal to nRT. Here, P is constant. So that means if I take delta of everything here, the P will get out. So I'll have P delta V, which is just nR, which is a constant delta T. So basically, delta T is just what? P delta V. P, it's constant, that's why I'm putting it out, and delta V divided by nR. And this, I will take it, and I will plug it here. I will have what? N Cp. Now delta T, I will have P delta V divided by nR. The N goes away, Cp divided by R. So you remember here, it's a mistake. This CV, but this is Cp. So Cp divided by R is just 5/2. So QBC is just 5/2. Cp divided by R, the N goes away. So P delta V. So this is my heat during this process BC. So let me put the numbers. It's 5/2. What is the pressure? It's constant. It's pressure B or pressure C, which is 1 atmosphere. So I multiply 1. Multiplied by 1.01, of course, 10 to the power 5 Pascal. multiplied by delta V. It will be V final minus V initial. V final is VC. Basically, you will have 10. V initial is VB, which is 50. But you put it in meter cube, right? 10 to the power minus 3 meter cube. And if you calculate this, how much do you get? If I'm not mistaken, I get 10,100 joule. And you see, this is QBC, and it's negative. You see, during this process, BC, heat is released, so it's going out. Okay? This means in, QAB is going in, QBC is negative, it's getting out, QAB is positive. Now, finally, what is QCA? That's question number C. Basically, what is QCA? So how do we get QCA? So I'm in question number C now. QCA, it's a constant volume process. Okay? Isovolumetric or isochoric process. So it's just equal to N CV, specific heat at constant volume multiplied by dT. Okay? But the same problem as before, what is delta T? Well, now it's a constant volume process. I know that PV is equal to nRT. Okay, now if I take delta for everything, now the volume is constant, so it can get out. So volume is getting out, and I will have delta P is just equal to nR delta T. That means that my delta T, this case for constant volume process, is just constant volume multiplied by change in pressure divided by nR. So this, I will plug it here. Okay. So let me erase this. So I will have some. I need to erase this. Okay, let me erase everything. So I'm in question number C. What is QCA? As I said, and CV delta T. But the delta T, we already got it, okay? And CV delta T will be what? As we said, it's V delta P divided by nR. The n goes away. So I will have CV divided by R multiplied by V delta P. So CV divided by R is just 3/2 because it's a monoatomic ideal gas, as we said before. V, I know it, it's constant. So this is, so V is constant, V is 10 liters. So 10 to the power minus 3 meter cube. And what is the change in pressure? So it will be P final minus P initial. P final is PA. So 5 atmosphere minus PC, which is initial pressure, which is 1 atmosphere. Now atmosphere is just 1.01. So let me write it here. An atmosphere is 1.01 to the power 5 Pascal. So when you calculate this, you get what? So you get plus 6,060 joules, and it's positive, okay? So the heat here is absorbed by the gas, so it's getting inside. Okay, so here heat was positive, it's QAB, and here heat is released, so it's getting out, QBC. This is positive, this is negative, this CA is positive, so it's getting in. Okay, good. Now, question number D. Calculate the heat added to the gas as, the heat added to the gas. So what is QH? So during this cycle, heat is added to the gas. Calculate QH. What is QH? Of course, QH will be all the positive heats. It will be QAB plus QCA. And this is heat added to the gas, so absorbed by the gas, so positive for the gas, okay? And we already calculated this before. AB we already calculated. If you calculate both of them, you add them, you get 14,187.66 joule. This is QH. Now E, calculate the heat lost by the gas as heat during this cycle. Of course, here, QL is just QBC, okay? So this is QL, QBC is QL. Okay, during the cycle, I'm adding QAB and QCA, but QBC is lost. So this is heat lost. Heat lost will be just equal to minus 10,100 joules. So now calculate the net work done by the gas, okay? Net work done by the engine, which is the net work done by the gas during one cycle. You know that the network here will be what? Positive, because you see my cycle is rotating clockwise. So the network is positive. That's why it's a heat engine, right? Otherwise it will be a refrigerator, but here it's a heat engine. Network is positive. What is network? It's just absolute value of QH minus absolute value of QL. So it will be 14,157.66 minus 10,100 joule. So this work, absolute value of work, of course, work is positive, will give you 4,087.66 joule. This is the work. Now, what is the efficiency of the engine? That's the last question. So epsilon is a heat engine. The efficiency will be just work, what I get, what I use, what is useful. By the way, the work, as we said, is this area here. And as we said, it's positive because we are rotating clockwise, divided by QH, the heat absorbed, the heat that my engine is taking from the environment, which is 4. So basically I have 4,087.66 divided by QH. What was QH? 14,187.66. And that will give you an efficiency epsilon of 28.8%. Okay. You see this problem? It reviews everything that we have done so far. Okay. So it's an excellent problem to review chapter 18, chapter 19, chapter 20. Okay. Good. Now, if you want to go further, I can give you a Stirling engine. You remember a Stirling engine, right? And I ask you to calculate basically, so let's say my Stirling engine is like this. Okay. And I give you the difference, the different pressures and volumes. And you can answer. So this, let's say this is A, B, C, D. You have 4 paths, right? And I ask you to calculate the heat for each of them. So for each path. So I can ask you to calculate QAB, what is QEC, what is QCD, and what is QDA. And I will ask you also, get me the heat added to the gas, and get me the heat lost by the gas, and get me the efficiency. Okay. You follow the same path, you can get what is the efficiency of a Stirling engine. Stirling engine. Okay. Anyway, that's just for those who want to go a little bit further. So the solution is given, as you can see. So this is a detailed solution. Check it out. Okay. And this is my efficiency, 28.8%. Okay. Good. Now, this problem, please solve it. It's an extremely important problem. So we have ice cube, 8 grams. You put it in kilograms, which is at minus 10 degrees Celsius. So I put it in a thermos flask containing 100 centimeter cube of water at 20 degrees Celsius. Now the question is to calculate the entropy change, the change in entropy for the cube water system when the equilibrium is reached. I give you specific heat of ice, specific heat of water, you know it already, and also you know the heat of fusion of ice. So this is extremely important, okay? So the process is irreversible. So I know that for the fact delta S will be positive. Now delta S, I have to first calculate the delta S for the ice. I have to also calculate the delta S for the water. Okay. But now here the water is not a reservoir. So it's not a reservoir. So the water here will cool down. So first I have to get what is the final temperature. Okay, so I take ice at minus 10 and I mix it with water at plus 20. What should be the final temperature? This was like the quiz I gave you. So heat absorbed by ice to melt will be heat released plus heat released by the water will be the same in absolute value. Okay. So I will let you solve that. First, you get what is TF. So you say that heat absorbed. So of course, the ice will go from minus 10. Then it goes to 0 ice, then 0 water. Then it will end up at T final. Well, this T final will be, of course, between 0 and 20 degrees Celsius. I know this because I did the calculation before, so it will be, this is small, so the water will be dominating. Okay, so the final state will be between 0 and 20 degrees Celsius. So all the ice will melt. So this is for ice. For water, it will leave 20 degrees Celsius and it will end up at TF. Okay, so first you get me this TF. What do you say? Of course, you will say that Q absorbed by ice plus Q lost by water. This is equal to 0. What is Q absorbed by ice? You will have mass ice, C ice, T final minus T initial. So this is the first thing here. So it will be 0 minus 10. And then I will have heat of transformation mass ice LF plus mass ice C water now. So this part T final minus 0. And this plus mass water. By the way, what is the mass of this water? You know that the density of water is just a gram per centimeter cube. So this mass of water is just 100 grams. You put it, of course, in kilogram. 1 kilogram. So mass water, C water, T final, but I don't know, minus the initial, which is 20. And I solve for T final. Okay. Now, once I get T final, and if I remember correctly, well, T final will be giving you something like 12 degrees. Okay. Once I get T final, now I calculate the change in entropy for the ice. Okay. So the ice, first I will have what? Mass ice, C ice, length of what? 273 divided by 263 plus mass ice LF divided by 273 plus mass ice C water length T final in Kelvin divided by 273. Okay. And then I can do the same for water, ds water. will give me what? Mass water, C water, length T final, and T final will be in Kelvin, 12 degree in Kelvin. So basically 285 point something in Kelvin divided by the initial, which is 293 Kelvin. Okay, and then you add them. Okay. So we already solved this problem. I don't know, well, I already solved it. So solve it again. So this is what we did here. Okay, so we find the final first, and then we calculate. Okay, this is for the water, and this is for the ice. Change in entropy, and you see that the change in entropy is positive, of course, because it's an irreversible process. So I let you solve the rest. Okay, please solve this problem, solve these problems. Okay, solve these problems. I give you the solutions. Okay, so solve them. The solution is given. Don't just watch the solution. Read the problem, try to solve it in 5 minutes, 6 minutes. And then if you don't see a way, you look at the solution and then you see what was the flaw in your way of thinking, okay, and how you can improve that. Okay, in the exam, you'll have enough time. So solve problems, solve problems, solve problems. I want you to solve this problem. I want you to solve these problems, but I gave you the solution, okay? Now, from what we have solved already, you can solve any problem. The rest is just practice, practice, practice. It does not make perfect, but it makes progress. Thank you very much and see you next time. Assalamu alaikum.